Electrochemistry is the study of how electricity interacts with chemical reactions. At the heart of this field lies the concept of electrode potentials. Imagine a battery. It has two terminals, a positive, plus, and a negative. These terminals are connected to electrodes, which are conductors immersed in an electrolyte solution. Each electrode, along with its surrounding electrolyte, forms a half cell. Within a half cell, a chemical reaction takes place, involving the transfer of electrons. This transfer of electrons creates a potential difference known as the half-cell potential. It's like a measure of the tendency of a particular half cell to either gain or lose electrons. However, we can't directly measure this potential for a single half cell in isolation. It's like trying to clap with one hand. To measure this electrical potential, we need a reference point, a standard against which we can compare all other half cells. And that's where the standard hydrogen electrode comes into play. The standard hydrogen electrode, or SHE, is a specially designed half cell that serves as our reference point in electrochemistry. It consists of a platinum electrode immersed in a solution with a hydrogen ion, H+, concentration of 1 mole per liter, under standard conditions of temperature and pressure. The SHE is assigned an arbitrary potential of 0 volts. This doesn't mean it doesn't have any potential, but rather, it acts as the 0 point on our electrochemical scale. Think of it like sea level. We measure the elevation of mountains and depths of oceans relative to this fixed point. But why can't we measure individual half-cell potentials directly? It's because electrical potential is a relative concept. Just like we need a reference point for measuring height, we need a reference electrode to measure the potential of another half cell. To determine the potential of a half cell, we connect it to the SHE and form a complete electrochemical cell. The potential difference measured across this cell is then attributed to the half cell being studied, as the SHE has a defined potential of 0 volts. This measured potential difference is known as the cell potential, or E cell, and is expressed in volts. It represents the driving force behind the flow of electrons from one half cell to another. A positive cell potential indicates a spontaneous reaction, while a negative value indicates a non-spontaneous reaction. Think of it like a tug of war. The half cell with a higher tendency to gain electrons, more positive potential, will pull electrons from the half cell with a lower tendency, less positive or more negative potential. The difference in their pulling power is what we measure as the cell potential. Understanding electrode potentials is crucial in numerous applications. Batteries, for instance, rely on the potential difference between two half cells to generate electricity. The greater the difference in their potentials, the higher the voltage the battery can produce. Electroplating, a process used to coat objects with a thin layer of metal, also utilizes electrode potentials. By controlling the potential difference between the object to be plated and a metal electrode, we can deposit a uniform and controlled layer of the desired metal. Even in biology, electrode potentials play a vital role. Nerve cells transmit signals through changes in the electrical potential across their membranes. Understanding these potential changes is crucial for studying brain activity and developing treatments for neurological disorders. In scientific research, electrode potentials are indispensable tools. They help us predict the spontaneity of chemical reactions, determine the equilibrium constant of reactions involving electron transfer, and even understand corrosion processes. Researchers use electrochemical techniques to study reaction mechanisms, develop new sensors for detecting various analytes, and design new materials with tailored properties. For instance, in the development of fuel cells, scientists explore different electrode materials and electrolytes to optimize the efficiency of energy conversion. Furthermore, the study of electrode potentials has led to the development of important analytical techniques like potentiometry. This technique utilizes the measurement of electrode potentials to determine the concentration of various ions in solutions, finding applications in environmental monitoring, food analysis, and medical diagnostics. Electrode potentials, with the standard hydrogen electrode as our reference point, are fundamental to understanding the interplay between chemistry and electricity. They provide insights into the driving forces behind chemical reactions, enabling us to predict their feasibility and manipulate them for various applications. From powering our devices to understanding biological processes, electrode potentials impact our lives in countless ways. As we delve deeper into the intricacies of electrochemistry, we unlock new possibilities for technological advancements, environmental solutions, and advancements in healthcare. Understanding this fundamental concept paves the way for a brighter, more sustainable future.